Hello and welcome back. Today I want to continue looking at rectifier bridges and active rectification by performing some experiments. Last time we looked at various theoretical aspects, how various implementations of rectifying bridges work in a circuit simulator, and today I want to reconfirm those observations with a set of practical measurements. So if you're curious about that and much more, then keep watching. So let's start things off by taking a look at the setup that we will be using today. So what I have here is a power supply, so this is a transformer providing 6.3 volts AC. This is the voltage that we will be trying to rectify today. This voltage is being measured on my third channel, so this blue line. It's not very sine wavy, but it will do. Next thing that we're measuring is the current that's being pulled by the circuit. So I'm using my old current probe that I built a long time ago, so this is this green line, and my circuit, I will be swapping between various rectifying bridges, and we will be supplying a 51 ohm power resistor, so this will be today's load. Now, the final thing to measure is the voltage that is reaching the resistor, and for this I'm using two oscilloscope probes and the differential mathematical function in the oscilloscope. So I'm subtracting the voltage on channel 2 from the voltage measured by channel 1. And it is important to mention here that because the input and the output are separated, there's no common point in between them, you can't use the same ground from which to measure all of the voltages. You either take the minus point on the output, or you take one of the lines on the AC input. You can't only use single-ended probes. On one side or the other, you will need to perform a differential measurement. Now, you can either use a differential probe if you have one. If not, you need to use the oscilloscope's subtract function. Now, the last thing to mention about the setup is that since I'm using my current probe, which is not the best thing ever, one of its problems is that it's quite noisy. So if I set my oscilloscope into normal mode, we can see just how noisy the measured current is. But since we're working with nice and periodic signals, we can take advantage of the oscilloscope's averaging function. So usually in your acquire menu, you do have the option to perform averages in between multiple captures. So right now it's set to 16. So what the oscilloscope is doing, it's taking 16 captures and then averaging out the values. So now my current measurement looks nice and clean. So let's start things off with something simple. I prepared two rectifying bridges built with similar rated diodes, so 2 ampere diodes in SMB package, but one bridge has PN type of diodes and the other one is built with Schottky type of diodes. So let's see if there's a difference in the voltages that arrive at the load using the different types of diodes. So to perform this measurement, I set both the input voltage and the output voltage to have the same exact reference and the same exact voltage scale, so we can measure the difference between input and output voltage. So if we turn on the input supply, I placed in the rectifier that has the PN type of diodes, and we let the output voltage stabilize using our cursors. So one marks the peak voltage on the output on the white line, the other one marks the peak voltage on the input, and we can see that we have about 1.6 volts of voltage difference between the two. So we have roughly 0.8 volts dropping on each of the diodes. Now, if we swap out the bridge and put in the one with Schottky diodes, input voltage stays the same, that doesn't change. But the output voltage, we can already see that it's above the marker line that we had previously. And if we just go to check out where exactly it is, it's at about 1 volt lower than the input voltage. So the Schottky diodes, we are getting about 0.5 volts drop on each of the diodes. So with Schottky diodes, we are getting higher output voltages and better power efficiency. But before moving on to other rectifying bridges, let's check out one more feature. So what happens with temperature? Now, the diodes, to a certain extent at least, will heat up by themselves from the current passing through them. But just to perform a easier to follow experiment, I will also be using some hot air to heat up the diodes and some cold spray to cool them down. So let's revert back to the first rectifying bridge, the one with PN diodes. So I'm using this one because the voltage drops are higher, so any effect that happens will be a bit more visible. Let's just put back the cursors, wait for the circuit to stabilize a bit. So we're back to our 1.6 volts of voltage drop on all of the diodes. And well, first of all, we can cool things down. So if we just spray some cool spray on it and we wait a bit, we should be getting smaller output voltages, so larger differences. And we can almost see that our output voltage is a bit lower than the reference line that we placed at the beginning. So when the diodes were at about 25 degrees Celsius. But now let's try to heat things up. So using some hot air, I set my hot air machine to about 160 degrees Celsius, so hopefully nothing melts. And if we heat up the diodes now, so I'm trying to uniformly heat up all of the diodes, we should be seeing the output voltage increase and well, the voltage drop decrease. So slowly but surely you should be seeing the white trace go above the reference line we put in place at the beginning. So the hotter the diodes are, the smaller the voltage drop, and the more efficiently the circuit will be running. And of course the exact same behavior will occur on the Schottky diodes, it's just that it's not as visible as it is with the PN junction diodes. So the lesson that we should be taking from this is that keeping the components hot is a good thing. Well, sort of. Increased temperature usually decreases the lifespan of your components, but as long as you manage to keep the components and surrounding circuitry in the safe operating region, under all use case conditions, you should be fine. But there's one last temperature dependent phenomenon that is important to keep in mind with diodes. Reverse leakage current. So even though a diode should block any sort of reverse current, it doesn't do a perfect job. And just how bad it is at its job is a temperature dependent phenomenon. And also diode type dependent phenomenon. Now, if we check the datasheet of a PN diode, so this is the S2 series, so the diode that we're using today, we get this typical instantaneous leakage current versus reverse voltage graph. So here we see the reverse voltage that can be applied up to a maximum of 100%, so this is percentage expressed in reference to the reverse voltage rating of the diode, and then the reverse current that we will be getting. And of course this is temperature dependent. The hotter the diode is, the higher the reverse current. And with this particular diode at 125 degrees, at 100% of the rated voltage, we are getting about 60 microamps of reverse leakage current. Not bad, not terrible. But now if we look at today's Schottky diode, so the 2 ampere 100 volt rated MBRS 2H100, and we look for the same graph, so we see the same reverse voltage versus reverse current at 125 degrees and 100 volts, so 100% of the rated reverse voltage. With this diode, we are getting almost 2 milliamps. So completely different order of magnitude compared to the other diode. So reverse current is temperature dependent and is usually current dependent. So the current rating of the diode. Usually higher current rated diodes will have higher reverse leakage currents, since the die in the diode is much larger. But now let's move on to something a bit more interesting. So today's active diode circuits. First circuit that I prepared looks something like this. We have 2 Schottky diodes that prevent both reverse voltage and reverse current, and then 2 simple transistor based diodes which only prevent reverse voltage. So these are built with N-channel MOSFETs, the gate is tied to the other input terminal through a resistor, and then there's a Zener diode to protect the gate source from exceeding voltages. So in this case, this is a 15 volt Zener diode. And the other circuit for today is a bit more complicated, so we can split it up into 2 halves. On the left half, we have a 4 transistor based rectifying bridge. So on the top side 2 p-channel transistors, on the bottom side 2 n-channel transistors. These will block negative voltages but will not block reverse current. And then this 5th transistor with its op-amp is used to also block reverse current. So here the op-amp is used to measure on the one side the output voltage and on the other the input voltage. and only when the input voltage is higher than the output will the transistor be activated. The rest of the components are various protection elements and, well, some predispositions for offset setting. So now we can test these circuits out, starting off with the Schottky bridge. So just to get a reference, I set my markers to show exactly the voltage drop we're getting with the Schottky bridge, so we can compare the other bridges to this one. So we are getting, as before, around 0.88 volts of voltage drop on the Schottky bridge. So if we swap this one out, first of all put in the half-active bridge, so the one that has two Schottky diodes and two transistors. We wait for the output voltage to stabilize, and if we use the cursor, we can see that we are getting about 0.48 volts of voltage drop on this bridge. So this is the voltage drop equal to half of what we were getting on the old Schottky bridge, about 0.44, and whatever is dropping on the transistor diode, so an extra few tens of millivolts. Now, the other thing that we can try out with this bridge is what happens when we add a capacitor. So right now the input current is positive when the input voltage is positive, negative when the input voltage is negative, since we're measuring it directly on the input. So current is only going from the power supply to the load. Now, if we add in a capacitor, we can see that the waveforms are changing a bit. The output voltage in white starts to become a bit more stable, so it doesn't oscillate as much as before. So this is the buffering action of the capacitor. And we can also see that current is only passing for a short period of time. So we have a large current spike when the power supply is charging the capacitor, and then when the capacitor voltage in white is larger than the input voltage in blue, there is no current. And again, current is still passing one way, coming from the power supply into our load. So now let's move on to our more complicated rectifying bridge. So the one that has 4 transistors and then the 5th one with the comparator. So first of all, I assembled it without the capacitor, and if we use the cursor, we can see that the input voltage and the output voltage are almost identical now. So we're barely getting 100 millivolts or something of voltage drop. So this is the big advantage of such a rectifying bridge. But now, if we also add in the capacitor, we can still see our small voltage drop appearing. The output voltage is a bit more stable, but we see an interesting phenomenon on the current waveform. So we have our forward current, but we also have this spike appearing. So what this is showing us is that even though we have positive voltage, we have negative current. So our active diode isn't doing a very good job. It's allowing current to pass into the load, so this positive half, but this little spike indicates that the transistor is not switching off fast enough, and it's letting some current go the other way. So this is just one of the problems that you can get with an active diode circuit. So either because of the offsets in the op-amp or because of certain delays occurring in the measurement circuit, the diode might not switch off fast enough, and you will be getting this sort of reverse current effect going on. Fortunately, with this particular op-amp, we do have a predisposition for some offset setting resistors, and if we add in an 100 kilo ohm resistor on one of these lines, and we put everything back together now, we can see that our reverse spike has almost completely disappeared. Now, even though adding this 100 kilo ohm resistor helps in this case, if I would swap out the op-amp and get some different value of internal offset, you would probably need a different value of resistor to account for it. So in general, it's very important when building this sort of active diode circuit to choose very low offset op-amps or comparators, so you don't get this reverse current effect going on. Final topic to talk about is peak current. So especially when a capacitor is added on the output of the rectifier, the diodes will be conducting short bursts of high current, and the larger the output capacitor is, the larger this current will be. So when going for active rectification, you need to check that the voltage drop on your transistor under these peak current conditions is actually smaller than what you would be getting with a regular diode. Otherwise, there's no point in using an overly complicated circuit. Now, if we come back to our last active diode circuit, so the one with 5 transistors, all of the transistors do have a bit of on resistance. So adding all of these up ends up giving us a total of a few hundred milliohms. And at relatively low currents, this doesn't really matter, But when you have high enough currents, you will see an impact in the performance of the rectifying bridge. So with our 470 microfarad capacitor, right when we have this large current spike, so we have 200 milliamps per division, so it's almost a 1 amp spike, you can see that there is quite a bit of a difference between the input voltage in blue and the output voltage in white. So if we look at it strictly on a vertical scale, right at the end, at the peak voltage, where the current is small, this difference goes away, so you don't really see this in the global performance. Now, on the other hand, if we swap out this capacitor and go for a much bigger 2000 microfarad capacitor, so this should be pulling larger currents for shorter periods of time. And we just place this into the circuit, we can see our reverse current spike came back, so the fix that we applied was not sufficient. We still have a bit of an offset. We can see that we are pulling roughly 800 milliamps. The peak current didn't really change because of the various series resistances in the circuit, the transistors and the internal resistance of the capacitor. So we have an almost uniform current consumption, and we can see the effect of this in the output voltage. So now we have a consistent voltage drop on the rectifying bridge throughout the conduction period. So if we take our cursors a bit, we are getting about 280 millivolts of voltage drop. So if we would increase the capacitance even more, we would be getting much larger currents, and the outcome would be that the performance of this bridge would be similar to that of the bridge that had 2 Schottky diodes and 2 transistors. So if your transistors don't have a small enough on resistance, the complexity of the circuit will not really be worth it. Now, there are 2 things that can be done here. On the one side, you can use better, so lower on resistance transistors, which is usually a very expensive solution, or you can try to reduce the peak current by applying some power factor correction methods, the simplest of which being the addition of an inductor. And to illustrate this, I prepared the simulation in LDSpice. So here I just left a single diode to keep things simple. We have a reference circuit with a sine wave going through a diode, supplying a load with a buffer capacitor, and then we have the same circuit that also has an inductor in series. So if we run this thing, we can see that we're getting about 1.45 amps of peak current through the diode when there's nothing, but when we also add the inductor, we are getting a lower peak current. But the conduction current is also spread out a bit more. So the diode is conducting for a longer period of time. So the idea with this inductor is that when your input voltage is rising, current is rising, the inductor is opposing this increasing current, so it stores energy, and when the input voltage is dropping, and also the current is dropping, the stored energy in the inductor is being released. So in effect, you're getting smaller peak currents over a wider period. Now at 50 Hz, frequency is extremely small, so you would normally need very large inductors to obtain power factor correction using this method. But in this case at least, even with a 220 microhenry inductor, combined with this 2200 microfarad capacitor, we do get a noticeable effect. It's not perfect, but it's a start. So now, I've set the markers to clearly mark out the extent of the current waveform, so where it begins, where it ends, so where it goes for 0, and the exact peak value. And now we can compare this to what happens when we add an inductor. So I have a 220 microhenry inductor here, and if I take out this interruption in the circuit and add in the inductor, we can see that our peak current is a bit lower. So we have the marker that was marking the peak current from before. Right now we're a bit lower. But we can also see that the current passes through 0 a bit later. So before it was about 3 milliseconds, right now it's just a bit more. Now the last thing to observe is that this upper marker I set to where we had the peak voltage before. And right now our peak voltage has decreased. So adding in inductors like this won't just have an effect on the current waveform, it will also have an effect on the voltage waveform. Now from a performance point of view, it doesn't really matter if the inductor is placed before or after the rectifying bridge. The resulting voltage will be the same. So here I placed both versions into the circuit simulator, inductor after the rectifying bridge and inductor before the rectifying bridge. If we run the simulation, we can see that both of these circuits on the load side are producing the exact same voltage profile. And well, we get the exact same current running through the two circuits. Now, where you do get the difference is in the behavior of the circuit when the power turns off. So first off, I prepared a circuit with the inductor on the output of the rectifying bridge and with a switch to interrupt the input supply. And from a timing point of view, the switch is turning off right at the point where the current running through the supply is maximum. And the reason for this is to see what happens with the inductor when you're no longer supplying current to it. So the current that used to pass through the inductor needs to go somewhere, it cannot just vanish, and the inductor will turn from a load into a generator. So the inductor will develop a voltage on itself, and what we can see is that the voltage before the inductor, so we had relatively 3.5 volts, and then when we got this interruption, the inductor discharged, producing a higher voltage. So the voltage on the load side isn't really affected, it's mostly the voltage on the diode side, but with the rectifying bridge before the inductor, the diodes are acting as flywheel diodes. So this current that was stored in the inductor gets conducted through the diodes and well, nothing bad happens. Now on the other hand, when the inductor is before the rectifying bridge and you suddenly interrupt the voltage, well, there is no place for the current stored in the inductor to go, and with this circuit we get a huge voltage spike going into the kilovolts range. So the inductor discharges by producing a high voltage. Now you can mitigate this spike quite easily either by adding a capacitor or a resistor. So for example, you can build a circuit like this where there's a say 100 nanofarad capacitor before the inductor, some resistor to discharge it, and with this circuit, when the power supply suddenly turns off, we still get the spike, but it's much more manageable. Point is, you need to take care when designing a circuit to not just look at how the circuit works under normal operating conditions, but also how it starts up and how it shuts down, since you might run into various effects. In the end, rectifier efficiency and active rectification are important concepts to keep in mind, not just from the benefits point of view, but also you need to consider the problems that they bring. If you want to use an active rectifier, you need to ensure that it will actually bring you benefits, because most often it will be considerably more expensive than using a classic rectifying bridge. But of course, under special conditions, you will have no other choice than to use this sort of circuit. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.